A NAND flash-based SSD itself is quite a complicated embedded system that contains multiple cores, hardware controllers, low-power DRAM, and NAND flash chips. The main reason for such high complexity is that NAND flash memory has various unique characteristics, such as erase before write property, limited endurance, and high error rates, which do not exist in traditional hard disk drives. So in the SSD controller, sophisticated system software runs on multiple embedded cores while interacting various hardware controllers to provide backward compatibility with hard disk drives and hide the unique characteristics of NAND flash memory. To recap the unique characteristics of NAND flash memory, let me start from some fundamental basics of NAND flash memory. A flash cell stores data using its threshold voltage level, which is dictated by the amount of electrons or charge in the cell. It means that a flash cell can change its threshold voltage or charge level in a non-volatile manner. Programming a cell increases the cell's threshold voltage level, while erasing a cell decreases the cell's threshold voltage level. So a flash cell encodes data using these different threshold voltage states. So for example, we can read a cell as 1 if its threshold voltage is lower than the reference voltage level, and otherwise it would read as 0. If we make only 2 threshold voltage states, a cell can store only a single bit. But with more precise threshold voltage control and more reference voltage levels, we can store multiple bits in a single cell, which is called a multi-level cell technique. And unfortunately, a flash cell leaks its electrons over time, which is commonly called the retention loss. In this example, we can still read the correct data from a cell after 1 year retention time, 0, 1 here, because the cell's charge level is still higher than the reference voltage level, right? However, a very long retention time, 2 years in total in this example, can decrease the cell threshold voltage to be lower than the reference voltage level, which in turn introduces a retention error. Finally, a flash cell has a limited lifetime, meaning that it cannot reliably store the data after experiencing a certain number of program and erase cycles, or PE cycles in short. For example, at a 1 kp cycle, a 1 year retention would unlikely introduce a bit error, but at 10 kp cycle, the same amount of retention time would very likely cause a bit error. Okay, now let me recap the NAND flash organization. A core operating principle of NAND flash memory is that a large number of flash cells operate in parallel. So a single word line controls more than 100,000 flash cells, meaning such a large number of cells in the same word lines are read and programmed at the same time. And more than hundreds of word lines comprise a NAND flash block, and all the cells in the same block are concurrently erased. And this design increases the operational latency of NAND flash memory for sure, but also enables the significantly high operation bandwidth of NAND flash memory because the latency increases sublinearly with the number of cells operating in parallel. But another problem is that because of this, NAND flash memory cannot efficiently support overwrites to a programmed word line. Meaning that we needed to first erase the entire block before writing any new data, which is called the erase before write property. For sure, we can issue a program command or program the word line because NAND flash is just a passive memory device. But in most cases, doing so cannot store the correct data. This is because it is impossible to override a 0 cell to be a 1 cell. For example, the second cell in word line, making this cell to be 1 cell requires to decrease the cell threshold voltage level. But as we discussed, the program operation can only increase the target cell's threshold voltage level. So to update the second cell in this case to store bit data 1, we needed to erase the cell, which requires to erase all the cells in the block. Usually we describe a NAND flash block to have multiple pages where each bit of a page is stored in 1 cell of the corresponding word line. And if we store 3 bit, if we store 3 bits in a single flash cell, meaning that a word line stores the 3 pages, which we call triple level cell or TLC NAND flash memory, we can increase the number of pages per block without changing the cell array. Okay, I think I covered every necessary background now. Okay, do you have any questions so far? Okay, hope everything is clear. So now let's dive into the first work entitled Reducing Solid State Drive Read Latency by Optimizing Read-Retry, which was presented in ASPLOS last year. Okay, this work tackles the long and non-deterministic or unpredictable read latency of modern NAND flash-based SSDs. Ideally, for reading 4 KB data from an SSD, we usually expect its latency to be around 100 microseconds. But in reality, it often takes more than 1 millisecond, which significantly degrades the quality of service of read-intensive, latency-sensitive applications. So what is going inside the SSD? In fact, there can be many possible reasons for this latency fluctuation, but one key reason is an internal process of modern SSDs called read-retry. For an incoming host request, the SSD firmware, which is commonly called the flash translation layer, or FTL in short, it sends a read request to the target chip through the flash controller. The problem is that sometimes the SSD retries the same read command again and again, which increases the read latency linearly with the number of read retries. Then why does the read retry happen? In fact, read-retry is essential to guaranteeing data reliability of modern NAND flash-based SSDs. So this shows the threshold voltage distribution of a page. For a recap, the x-axis indicates a cell's threshold voltage level, and the y-axis indicates the number of cells that have a certain threshold voltage level. So for example, a coordinate x, y means that the page has y cells whose threshold voltage level is x volt. Okay, and why do we use such a distribution? As we discussed, the flash cell stores data using its threshold voltage or charge level. So if a cell's threshold voltage is lower than the reference, it reads as 1, and otherwise it's 0, right? But as discussed, the NAND flash memory reads and writes data in page granularity, and it is practically impossible to make all the cells in a page have the same threshold voltage levels, since the physical characteristics such as cell size significantly vary across the cells due to process variations. So a page's program status is commonly described as a distribution like this. The problem is that in NAND flash memory, for various reasons, such as retention loss and program interference, the programmed threshold voltage states shift and widen. If a threshold voltage states shift beyond the reference voltage level, for example, here, see this red area, reading the page incurs error as the cells in this area would read as 1, which should be 0 actually. To avoid such errors, it is common practice in modern SSDs to use error correcting codes, or ECC in short, which basically stores some redundant data called the ECC parity along with the original data in order to use the redundant data for error correction. Typically, the ECC engine exists in flash controller, meaning outside of chip. And when the SSD controller issues a read request, for example, to page 0 in this figure, the flash controller issues a NAND flash command with the page address, and then the sensor data is transferred from the chip to the flash controller, and finally the ECC engine decodes the transfer data, trying to correct all the raw bit errors in the red page. Unfortunately, modern NAND flash memory exhibits a very high raw bit error rates due to the multi-level cell technique. So this is the threshold voltage distribution of a single level cell page, and this is for a triple level cell page where a single cell stores the 3 bits using 8 different threshold voltage states. And as you can see here, the TLC technique significantly decreases the margin between 2 adjacent threshold voltage states. It means that smaller, very small, even very small threshold voltage shift can cause bit errors much more easily, right? And due to this high raw bit error rate, modern NAND flash-based SSDs commonly adopt a very strong ECC, for example, which can correct up to 8-bit errors per 1 kilobyte data. But this is not scalable at all, as the stronger the ECC, the higher the latency, power, and area overheads. It means that we cannot increase the SSD's error correcting capability or ECC capability without limitation. So in modern NAND flash-based SSDs, actually it frequently happens that a read incurs more bit errors than the ECC capability, which in turn causes a data loss if there is no countermeasure. To address this problem, modern SSDs commonly adopt a read-retry, which basically reads the pages again with adjacent read reference voltage value. And as shown in this figure, using properly adjusted read reference voltage values significantly decrease the shifted area beyond the reference, these red areas, meaning the number of raw bit errors in reading the page. So basically, the goal of a read-retry step is to find a near optimal read reference voltage that would reduce the number of raw bit errors to be lower than the ECC capability. Unfortunately, read-retry also significantly increases the read latency. And as we discussed, the reading a page consists of 3 steps: page sensing at the chip, data transfer from the chip to the flash controller, and ECC decoding at the flash controller. So if the number of bit errors is lower than the ECC correction capability, the read request can be returned immediately after ECC decoding. However, when the number of raw bit errors is higher than the ECC capability, the flash controller performs a multiple read-retry step until it reduces the number of bit errors to be lower than the ECC capability. And this in turn increases the read latency almost linearly with the number of retry steps. Okay, now let me introduce our key ideas to reduce the read-retry latency. Our first observation is that in common case, once a read fails, multiple read-retry steps are required for correctly reading the page. So our first key idea, which we call pipeline read-retry or P&AR² in short, is that instead of waiting for the ECC decoding of each retry step, we start the next step as soon as the sensing operation at the chip is finished, speculating that the next retry step would be likely needed. And this idea is very simple, but can significantly reduce the read-retry latency by removing the data transfer and ECC decoding from the critical path, which actually contribute to almost 30% of the latency of each retry step. Okay, now let me introduce our second technique called adaptive read-retry or AR² in short. Our another key observation is that when read-write eventually succeeds, there always exists a large ECC margin in the final retry step due to the use of a near optimal read reference voltage. In this figure, for example, there are only 23 bit errors in the final retry step, while the ECC can correct up to 72 bit errors. And we think, can we leverage this reliability margin to reduce the read-retry latency? And the answer is yes, for sure. So the key idea of AR² is to trade the large ECC margin in the final retry step for reducing read timing parameters, meaning the read latency for each retry step, which can further reduce the read-retry latency on top of P&AR². You may notice that the sensing latency of each retry step is significantly reduced compared to regular read, at the cost of increasing raw bit errors. So here E1, E2, and EI indicates the additional bit errors that caused by the reducing the read time parameters. Here I would like to emphasize that AR² reduces the sensing latency of every retry step, while ensuring that this reduction would not cause the number of raw bit errors in the final retry step to exceed the capability, meaning that reducing these timing parameters should ensure that the final retry step's raw bit error rate is below the ECC capability. This is really important because otherwise AR² would rather increase the read-retry latency by causing additional read-retry steps. And here, we only care about the final retry steps, as the other previous step here would fail anyways, even if we did not reduce, meaning that if we used the regular read timing parameters. Okay, we validate the feasibility of AR² using 160 real TLC in the flash chips, and we observe a large ECC margin in the final retry step, even under worst case operating conditions due to the use of a near optimal read reference voltage. And there is also a large reliability margin that manufacturers incorporate into read timing parameters, considering worst case operating scenarios. So we conclude that AR² can easily work in commodity NAND flash chips, enabling at least 25% reduction of the page sensing latency for every retry step. Okay, let me review the overall design of our P&AR². Sorry about that. We first propose SSD manufacturers to incorporate a read timing parameter table in their SSD so that the SSD firmware can get the best read timing parameters depending on the current operating conditions, such as PE cycles and retention time. So when a read failure occurs, the flash controller notifies it to the SSD firmware, and then the SSD firmware queries the table with the current operating conditions to send the best timing parameters to the flash controller. The flash controller performs a read retry with the reduced timing parameters, meaning that it uses AR² while speculatively starting the next retry step, meaning that it also uses a PR² until the ECC decoding succeeds. Finally, the flash controller sends the correct page data to the user through the SSD controller. Okay, so the key takeaway here, which I think is quite interesting, is that modern SSDs employ strong ECC to avoid the read retry as much as possible because, yeah, its performance penalty is so significant. But it is impossible to completely avoid the read retry. But once read retry occurs again, the strong ECC can also provide a high reliability margin that can be used to reduce the read retry latency. Okay, for our system level evaluation, we use a state-of-the-art SSD simulator called MQSIM and 12 real-world workers. And our results show that our proposal improves SSD response time by up to 51% compared to a high-end SSD that has no read-retry mitigation, and by up to 30% compared to a state-of-the-art read-retry mitigation technique. Okay, so any questions so far? Okay, so let me let me move on to the next work to support efficient data sanitization in modern NAND flash-based SSDs. Okay, here is the full title of the paper, and it was presented in ASPLOS 2020. And this work tackles the Data-Remanence problem, where even when the user deletes stored data, the data can remain inside the SSD for indefinite time. And so this shows a very brief description of a NAND flash-based SSDs, a storage system, okay? Because we are also describing the file system also. Okay, suppose that the user updates a file A by overwriting A1 prime. Okay, and as we discussed, NAND flash memory does not support overwrites, so common SSDs always perform out-of-place updates, leaving the old data A1 intact. It just marks the original data A1 as invalid. And let's assume that the user writes another file to the SSD and deletes it very soon. Then the SSD does not erase the related pages immediately, while just marking them as invalid also. So then the question is, when would such pages be erased, right? And the answer is that a page is physically erased only in garbage collection that is triggered only when the SSD is running out of free pages. It means that if the user does not write any data for a long time after this, the invalid data, invalid pages remain in the SSD indefinitely. And this is the fundamental source of data recovery attacks that aim to disclose private data, which has been already deleted or updated by the user. So since the user explicitly updated and deleted the data from the file system, the system must guarantee that the data is inaccessible, right? However, if an adversary can detach the SSD from the system and desolder the chips from the SSD, then the adversary can directly access the chips with the custom flash controller to get all the invalid data remaining in the chips. So, and finally, by using existing forensic tools, the adversary can easily completely recover all the versions of updated or deleted files. The most intuitive way, for sure, to prevent such data recovery attacks is to immediately erase an invalid page. However, as we discussed, the eraser unit of NAND flash memory is a block which contains more than 1,000 pages these days. So to erase a target page, we should first move all the valid pages in the corresponding block to another free block, which causes a significant performance overhead, especially when the target block has many valid pages. Also, if the target block has some free pages, they should be also erased without programmed, which wastes P cycles. So in conclusion, immediate block erasure is hard to use in practice due to its prohibitive performance and lifetime overheads. To address this, prior work proposed a data sanitization technique called scrubbing. The key idea of scrubbing is to reprogram all the flash cells that store an invalid page. It means that instead of erasing all the cells, scrubbing reprograms all the cells to be 0 cells. So overwriting is impossible for sure in NAND flash memory as discussed in most cases, because program operations can only increase the cell's threshold voltage, but making all the cells to be 0 cells is certainly possible, right? And like this, scrubbing can destroy the page data without block erasure. So when this technique was first proposed more than a decade ago, the problem seemed to solved. However, scrubbing is also hard to use in modern NAND flash memory due to 2 reasons. The first problem is that modern NAND flash memory stores multiple pages in a single word line using MLC techniques. So in this example, actually page 1 can be stored in a word line 0, not word line 1, along with page 0 and 2. Right? And if we assume the TLC technology. And in this case, reprogramming all the cells to the highest threshold voltage states would destroy not only the target pages data, page 0's data, but also the other pages data that share the word line, right? It means that in MS NAND flash memory, scrubbing also requires a copy operation to avoid data loss for the other valid pages in the same word line. And even if we can somehow afford the copy overhead, because the number of copy operation required is relatively smaller the immediate compared to the immediate block erasure, but scrubbing has another reliability issue in modern NAND flash memory due to program interference to the adjacent word line. It means that reprogramming the target word line slightly programs the adjacent word line, which is called the program interference. And it creates the number of row-bit errors in the adjacent pages in modern NAND flash memory. So in conclusion, existing solutions that physically destroy data incur significant performance lifetime and reliability problems in modern NAND flash memory. Okay, let me introduce our key idea called Evanesco. So our key idea is to allow a NAND flash chip to be aware of the validity of each page so that the chip itself can avoid access to invalid pages. So the key point is Evanesco does not touch flash cells that store user data, so it can avoid copying valid pages and affecting the reliability of stored data. So to this end, we propose two new NAND flash commands, page lock and block lock, or P lock and B lock in short, respectively. So to sanitize a page, the SSD firmware sends a P lock command that disables the page's access information flag inside the NAND flash chip. And if a block needs to be sanitized, the B lock command disables all the pages in the block. And even if an adversary directly accesses the raw flash chip, the chip just returns dummy data, let's say all zero data, for any access to an invalid page. So there are two design requirements for Evanesco. First, the chip must keep the per chip access permission flags in a non-volatile manner. And we needed to put, and also we needed to put the access control logic inside the NAND flash chip, as the other system components like flash controllers and FTL can be compromised also by adversaries, as we discussed, right? So the key challenge here is that we need to make the area overhead minimal, as a high chip density is the paramount requirement in modern NAND flash memory. So let me introduce how our P-lock can meet these requirements. And in our paper, actually, we also propose B-lock, but high-level idea is quite similar. So I will skip B-lock in this presentation, but I would encourage you reading the full paper if you are interested. So to keep the first challenge is on-chip access permission flag at low cost. So to keep the per page access permission flags, we use the spare cells in each word line. So in addition to the cells to store the user data, a word line has also spare cells to store page-related data, page-related metadata, like ECC parity, as we discussed, right? Sorry, and we use some of these spare cells to store each page's access permission flag. So the access permission flag cells are initially erased when the page is first programmed, and P-lock programs only the target page's access permission flag. Okay, and as it does not program any data cell here, it has little interference impact on stored data. For sure, there would be some interference between flag cells, right? But it is not a problem because we use flag cells as a single level cell to store only one bit data, meaning enabled or disabled. And SLC cells are significantly more robust to the program interference compared to MLC cells. Okay, now we have a low cost on-chip access permission flag using spare cells. So the remaining problem is to implement on-chip access control logic at low cost. And we address this by slightly changing the data path of NAND flash memory. So in NAND flash memory, the stored data is first read to the page buffer through the bin lines and transferred out of the chip byte by byte throughout the data out circuitry. We slightly change this data path by adding multiplexer and bridge transistor, which changes the connectivity between the page buffer and data out circuitry depending on the read page's access permission flag. So in this example, the target page's access permission flag here is disabled, meaning its cell value is 0, which disables the bridge transistor and thus disconnects the page buffer from the data out circuitry. So reading the page always returns all zero data, regardless of actual values of stored data in page buffer, right? So, and we validated the reliability of Evanesco via real device characterization of 160 TLC NAND flash chips. And our results show that Evanesco does not compromise the reliability of NAND flash memory if we set the latency of P-lock and B-lock to be 100 microseconds and 300 microseconds respectively. Yeah, please see the full paper for our detailed design space explanation. So Evanesco enables efficient data sanitization without any copy operations and reliability issues via minimal changes to commodity NAND flash chips. However, the performance of RAID is still not negligible, as the P-log and B-log latency is as long as the typical page read latency, like 100 microseconds, let's say. So to address this, we also propose a SecureSSD, an Evanesco-enabled SSD that minimizes the performance overhead of data sanitization in 2 ways. So first, the log manager inside the SecureSSD issues PLOC and BLOC commands depending on the target block's status. So if the target block has many valid pages, it issues a PLOC command for each individual pages to sanitize. However, if the target block has no other valid page, but only invalid pages, so only pages to invalidate, it issues a BLOC command to sanitize multiple pages at once. The second optimization is cross-layer interactions for selective data sanitization. And we envision a system where the user application can inform the SSD of each data's security level through the file system. For example, when the user writes a security-sensitive file, the application sends the information to the SSD so that the SSD can keep track of the security level of related pages. So when the user deletes the security-insensitive file, the SSD performs neither PLOC nor BLOC operations, avoiding performance overhead due to unnecessary sanitization. Okay, for evaluation, we compare the performance of SecureSSD against the 2 SSDs, ERSSD and SCRSSD, which perform immediate block erasure and scrubbing, respectively, whenever a page is invalidated. And we normalized the performance of 3 SSDs to an unmodified SSD that does not support any data sanitization and thus has no performance and lifetime overheads. As the graph shows, the SecureSSD provides a comparable performance with an unmodified SSD, while existing solutions significantly degrade SSD performance due to a large amount of copy operations for valid pages. So SecureSSD significantly reduces the performance overhead of data sanitization. We also measure the write amplification factor of each SSD ensured to WAF value to compare the lifetime overhead. Basically, WAF indicates how many page writes the SSD needs to perform for servicing the same amount of host writes. So the lower the WAF value, the longer the lifetime of the SSD. And in y-axis, we also normalized the WAF value. I'm sorry about this. So something wrong in this figure, but yeah. So this is 1, 2, 3, 4, 5. So sorry about this mistake. And as you can see, existing techniques significantly increase the number of written page, the WAF values for in order to copy the while copying the associated valid pages. In contrast, as SecureSSD does not introduce any additional copy operation, it can provide the same lifetime as an unmodified SSD. Okay, let me conclude today's lecture with a summary of contributions. So the first work tackles the long and undeterministic SSD read latency due to an essential reliability management scheme in modern SSDs called the Read-Retry, which can significantly degrade the performance of a data-intensive application. So we propose a pipelined and adaptive read-retry that reduces read-retry latency by leveraging read-retry characteristics of NAND flash memory and ECC margin existing in modern SSDs. The second work tackles the data-remanence problem in NAND flash-based SSDs, where obsolete data can remain intact in the SSD for an indefinite time. So while existing techniques that physically destroy stored data exhibit prohibitive performance and lifetime overheads, our solution can efficiently support the data sanitization with minimal overheads by avoiding transfer of the obsolete data from NAND flash chips using existing spare cells and simple logic.
Okay, thank you for introduction. Hello, I'm Jisung Park, a senior researcher and lecturer at ETH Zürich. Today, I'm going to present our work, DeepSketch, a new machine learning-based reference search technique for post-deduplication data compression. I'd like to start with a high-level summary of this work. This work focuses on data reduction in storage systems, an effective approach at reducing the management cost of a data center by reducing the amount of data physically returned to storage devices. Among many data reduction techniques, post-deduplication data compression can maximize the data reduction ratio by performing data compression along with the traditional deduplication and lossless compression. However, we found that existing techniques provide significantly low benefits compared to the optimal because of their limited accuracy of reference search for data compression. In short, the existing technique often fail to identify any reference block for many incoming blocks that can actually benefit from data compression. To address this, we propose DeepSketch, the first machine learning-based reference search technique to generate a given data block's signature called a sketch, such that the higher the data compression benefit of two data blocks, the more similar the two blocks' sketch values. Our evaluation shows that DeepSketch significantly reduces the amount of written data compared to the state-of-the-art baseline. Here is the outline of my talk, and I'm going to start with a brief background on data reduction in storage systems. In this big data era, modern computing systems deal with unprecedented amounts of data. For example, it is known that Facebook generates more than 4 petabytes of new data every day. So data reduction is an effective approach to reduce the management cost of a data center by reducing the amount of written data to storage devices, which in turn enables the system to deal with the same amount of data with fewer or smaller hardware resources. Post-deduplication data compression combines the 3 different data reduction approaches to maximize the data reduction ratio. It performs a deduplication, data compression, and lossless compression in order, and is known to be able to achieve more than 2x data reduction over a simple combination of deduplication and lossless compression. Let me quickly explain how post-deduplication data compression handles the incoming write requests. Suppose that the system has an intermediate layer between the file system and the storage device, which we call a data reduction module. For an incoming write, the data reduction module first tries deduplication. If a write request has the same contents as a previously stored block, it skips writing of the requested data, but just maps the target logical block address to the identical block in order to serve future reads to the deduplicated block. If there is no identical data, the data reduction module tries data compression. Here, block Y is slightly different from block B. So if the data reduction module somehow can find this out, it performs data compression and stores the compressed data. In this example, the data reduction module also needs to keep the mapping information between blocks Y and B so that it can decompress the data compressed data for future read to block Y. Finally, if there is neither an identical block nor a similar block, the data reduction module just performs a lossless compression. The key challenge in post-deduplication data compression is how to find a good reference block for an incoming data block across a wide range of stored data at low cost. Scanning all previously stored blocks is infeasible for sure due to its prohibitive performance overhead. In fact, as explained, deduplication also requires to search for an identical block to an incoming block across the storage system. A common approach for this is to use a strong hash value to generate each data block's fingerprint, which enables a quick exact match search by comparing only fingerprints of data blocks. However, fingerprint is difficult to use for data compression, as a strong hash function is typically designed to generate significantly different hash values, especially for similar data blocks, in order to minimize the hash collision rate. So to address this, the prior work proposes a different approach called data sketching that generates a more approximate signature than fingerprint called sketch, such that two similar blocks have similar sketches. For example, the state-of-the-art techniques, which we call a super feature-based approach, can generate the same hash values for two data blocks that have a small difference from each other. This enables a quick identification of similar data blocks by comparing over the sketches of data blocks. However, according to our analysis, existing superficial-based techniques provide a significantly lower data reduction ratio than the optimal. For example, in a general PC usage workload, a superficial-based approach provides only 60% of the data reduction ratio of the brute force search. It turned out that the core problem is a high false negative ratio. In other words, the superficial-based approach is very good at generating the same sketch value for highly similar blocks, but different sketches. But it generates different sketches for data blocks that are not that so similar, but can still benefit from data compression. Next, I will introduce DeepSketch, focusing on its key idea. Our key idea is simple. So we use the learning to hash method, a promising machine learning-based approach for the nearest neighbor search problem. Let me briefly explain how a popular learning to hash method works for content-based image retrieval. It trains a deep neural network to classify a given image set and uses the last hidden layer to generate a binary hash value of an input image. If two images are similar enough to have the same inference result, it means that the activations in the last hidden layer are also likely to be similar, and so are their hash values. So basically, DeepSketch replaces the existing superficial-based sketch generator with a DNN-based sketch generator. While the key idea is simple, it was not that straightforward to apply the learning to hash method for reference search in data compression due to the lack of semantic information in our target dataset. To be specific, most prior learning to hash approaches deal with specific data types, but in this sketch, it needs to process a general binary data. Therefore, our target data has extremely high dimensional space, so it could be challenging to collect a training data set diverse enough to train DNN with high inference accuracy. So these challenges led us to perform clustering-based DNN training that first clusters an unlabeled data set collected from various real-world workloads and performs supervised learning using the clustering results. So we first cluster similar data blocks in the unlabeled data set and train a DNN to accurately infer a given data block's cluster. Then, using the learning to hash method, we can generate similar sketches for similar blocks. The first problem we encountered in this is that existing clustering methods are unsuitable for DeepSketch. For example, k-means clustering requires to properly set the number of clusters, saying the value of k, which is unfortunately unknown in our target dataset. Hierarchical clustering does not have such requirements, but it introduces huge computation and memory overheads for large datasets. So we propose dynamic k-means clustering, in short DK clustering, a version of k-means clustering that dynamically refines the value of k during clustering. The key idea is to iterate 2 steps until the clustering converges. In high level, the first step roughly groups the data groups at low cost while removing low-impact data blocks that have no similar blocks within the dataset. Then the second step finds the best mean block of each cluster and unlabels the outliers that are not similar enough to the cluster's new mean so that it can be clustered again in the next iteration. The second problem we had is the non-uniform distribution of data blocks across the clusters. For example, after DK clustering in our dataset, the largest 10% clusters contain about 48% of total data blocks, which can make our DNN training significantly biased towards specific data patterns. To address this, we resize every cluster from DK clustering to have the same number of data blocks by either randomly selecting data blocks or adding randomly modified data blocks, depending on the number of blocks in the cluster. After preparing the training dataset, we train a DNN as a sketch generator via two-step transfer learning, following the methodology of a state-of-the-art learning-to-hash method called the greedy hash. We first train a classification model that infers a given data blocks cluster and use the learned weighted value to train a hash network model that has an additional hidden layer to generate a blocks sketch. Through our hyperparameter exploration, we found a lightweight yet effective DNN model that consists of only 3 convolutional layers and 2 fully connected layers. Next, I will present our key evaluation results. We compared our DeepSketch with 2 baselines. The first one is a simple combination of deduplication and lossless compression, and the other one is Finesse, a state-of-the-art super feature-based reference search technique for post-deduplication data compression. We evaluated 11 workloads, 6 workloads that we collected while running different applications on real systems, and 5 workloads collected while storing Stack Overflow database. We used 10% of the 6 traces for training dataset, but did not use the Stack Overflow workloads in our training in order to see the generality of DeepSketch. So this graph shows the average data reduction ratio of Finesse and DeepSketch normalized to the simple combination of deduplication and lossless compression. We observed that DeepSketch provides a large data reduction improvement over the state-of-the-art technique. We also make 2 other interesting observations regarding the Stack Overflow results. First, DeepSketch can provide high benefits even when the workloads are not used in its DNN training, which shows its high generality for unseen workloads. Second, and this is something unexpected, but DeepSketch can significantly improve the data reduction ratio, even for workloads that cannot benefit from Finesse. Next, we evaluated the data reduction ratio when we combine DeepSketch and Finesse and compared the results to the optimal. We normalized all the values in this graph to Finesse. And we observed that the combined technique can provide higher benefits over both standalone techniques, which suggests that DeepSketch and Finesse can actually complement each other. But still, there exists a significant data reduction gap between the combined approach and the optimal, which we believe can be reduced in future work by developing a more accurate DNN model, as done for many other nearest neighbor research problems. As the last main results, this graph compares the write bandwidth of Finesse, DeepSketch, and combined techniques. The results show that actually DeepSketch introduces non-trivial performance overhead over Finesse. This is mainly due to the approximate nearest neighbor search approach that I did not explain in this talk, but we believe this overhead can be also mitigated in future work in various ways, such as hardware acceleration or more efficient data structure. Please see our full paper for more detailed analysis and evaluation. There, we provide an empirical study on super feature-based reference search, hyperparameter exploration for DeepSketch's DNN, and analysis on performance and space overhead, reference search patterns, and impact of a training dataset. Finally, I'd like to conclude my talk with a quick summary. In this work, we tackle the limited data reduction benefit of existing post-deduplication data compression technique and propose a new machine learning-based reference search technique that can significantly improve the data reduction ratio. We hope that our key ideas inspire many future studies going forward. And thank you for listening to my talk. I'd be happy to take any question from you.